What if I told you that the boundaries of what computers can and cannot do were all laid down decades before programming languages or modern machines even existed? Welcome to the theory of computation, not just a subject, but the soul of computer science. This is not a course in dry math. It's a lens, a blueprint of how machines think, solve, and sometimes fail. If you're new to this channel, don't forget to hit subscribe. Every week, we break down the most complex computer science concepts into simple, easy explanations, in far less time than your textbooks. If you don't subscribe, you'll miss the shortcuts that others are already using to learn faster. Don't get left behind. Hit subscribe now and stay ahead. Let me take you back. Before JavaScript, before C, before silicon chips, mathematicians sat down and asked one simple question that would shape the future. What problems can machines solve? And what problems can they never solve, no matter how powerful the machine becomes? Questions like these changed the world and gave birth to TOC. That's what the theory of computation, or TOC, is about. It's the mathematical study of what can be computed, and just as critically, what cannot. But wait, why should you care? Because TOC runs your world in the background, and you don't even realize it. When your compiler transforms your clean code into machine instructions, that's formal grammar straight from TOC. When Siri or Alexa interpret your sentence or voice command, that's automata theory and language parsing at work. Ever wondered why we can't build a perfect antivirus? It's due to inherent limitations. Still not convinced? Now, try this thought experiment. Imagine writing a program that checks whether any random app, yours, mine, or anyone's, will run forever or stop eventually. Seems simple, right? Wrong. That's the halting problem, and TOC proved it's unsolvable. Not just difficult, but literally impossible. No matter how much you try, no matter how many quantum chips you build, there's a hard wall, and TOC shows you where that wall is. TOC doesn't teach computation. It teaches limits of logic, of machines, of human knowledge itself. So, if you ever wondered why computers behave the way they do, or why they fail, stick around. Because in this explainer, we're about to decode the mind of a machine. Trust me, once you see what's inside, you'll never unsee it. Ever wondered how your keyboard knows you're pressing the right password? Or how Google detects whether a sentence is grammatically correct? Deep beneath all that, hiding quietly, are finite automata. Simple, beautiful, mathematical machines. And they're the bedrock of how computers understand patterns. Let's break this down. Imagine this. You're at a haunted mansion. You can only enter a door if you say a special password. Let's say it's ABC. Now imagine there's a guard at each door. Each guard listens to just one letter. If you say A, you're allowed into room 1. Say B, you're let into room 2. C, room 3. But here's the catch. You must say the right letters in the right order. One wrong move and you're locked out. Congratulations. You've just walked through a deterministic, finite automation, or DFA. At its core, a DFA is a machine that reads input, usually a string of characters, one symbol at a time and moves from state to state based on fixed rules. Think of it like this. A DFA is like a strict vending machine. If you press the right combination of buttons, you get your soda. Press the wrong one, nothing happens. No ambiguity, no guessing. Only one path. What if instead of one vending machine path, you had multiple possible paths? And your machine could split into multiple copies of itself and try all possibilities at once. Picture yourself at a giant theme park, and you've come at a crossroads with multiple paths. In real life, you'd pick one path and hope it's the right one. But in the world of automata, you could magically split yourself into multiple copies, explore all paths at once, and reunite at the end to see if any path reached the destination. That's non-determinism, a superpower of NFA. Non-deterministic finite automation. In a deterministic finite automation, DFA, the rules are strict. One state, one path for each input symbol, no guessing. But an NFA is like a movie scene where the hero can create parallel timelines. Every possible choice is explored simultaneously. If any of those timelines reaches an accepting state, the machine says, "Yes, I accept the string." Now, the epsilon NFA adds a plot twist: invisible moves. Picture walking through that same theme park and suddenly finding hidden teleportation tunnels you can use without paying a ticket or showing any symbol. These tunnels are epsilon transitions. They let you jump between states for free without consuming any input. That means in an epsilon NFA, you can be in multiple states at once. You can move instantly before even looking at the next input symbol. Let's go back to our haunted mansion. In a DFA, you say A and go to exactly one room. But in an NFA, when you say A, the system might go to room 1 or room 3, or maybe both in parallel. Sounds like cheating. Well, here's the kicker. DFAs and NFAs are equally powerful. Yes, even though NFAs look more powerful because they can guess and try multiple paths, anything an NFA can do, a DFA can do too. We just need to build a big enough DFA to simulate it. They, NFA and DFA, recognize exactly the same set of languages, regular languages. The difference? NFAs are often simpler to design, while DFAs are simpler to implement. And epsilon NFAs? They make certain designs even cleaner before we eventually convert them to DFAs. This brings us to one of the coolest parts of finite automata. Picture this. You're organizing a party and you want to know all the possible guess combinations that can show up. Subset construction is like listing all possible combinations of states that an NFA might be in at once. You take all possible sets of NFA states and treat each set as a single DFA state. It's like compressing chaos into clarity. Yes, this makes the DFA a bit bigger, but it becomes deterministic with no guesswork involved. And once you've got your DFA, there's one more step left. Now, imagine you've built this massive DFA, but it turns out some states are doing the same job. Redundant, duplicates, waste of space. So, what do? You minimize it, just like you declutter your phone storage by deleting duplicate photos. DFA minimization removes equivalent states that behave identically for all inputs. The results? A smaller, faster, smarter automation. This minimal DFA is often what compilers and interpreters use behind the scenes. Let's bring this home. Ever written code in C++ or Python? Before your code ever runs, the compiler tokenizes your code, breaks it into keywords, symbols, variables. Guess what powers that? Yep, finite automata. Each language keyword like for, if, while becomes a pattern that can be detected using a DFA. Your entire source code is walked through by a giant DFA built from regular expressions. Fast, precise, brutally efficient. Now, automata aren't just about accepting or rejecting inputs. Sometimes we want them to produce outputs too. Enter Mealy and Moore machines. Both are finite automata with outputs, but the difference? A Moore machine gives output based on the current state. A Mealy machine gives output based on the current state and input symbol. Think of Moore machines like status lights on a printer. Red if jammed, green if ready. Mealy machines? Think of voice assistants. They respond to what state they're in and what you say. And again, both models are equivalent in power. One is just more compact than the other. So, why spend all this time on these machines? Because this is how your tools work. Google Docs autocorrect is backed by state machines. Regular expressions in VS Code or Python's remodule? Finite automata. Network protocols, routers, even microcontrollers in your washing machine. All use finite state machines under the hood. This is not abstract math. This is how machines think. Not in magic, not in mystery, but in states and transitions in predictable logic. So, next time you type a password, swipe a card, or parse a sentence, remember, a tiny automation might just be running the show. Have you ever typed Control F to search for a word in a PDF? Or used !https:/::/ to validate a URL while coding? Congrats! You've already whispered the language of machines, the secret code beneath web searches, code editors, spam filters, and even AI prompts. That language is built on regular expressions, or regex for short. But beneath that practical utility lies something far deeper, a universe called regular languages. And together, they form the beating heart of a class of computation that is both powerful and beautifully limited. Let's decode it. Let's start with a question. If I gave you infinite strings made of just two letters, A and B, could you design a system that filters only those strings, which start with A, end with B, and never have two B's in a row? That system, that ability to define a rule of patterns, is what a regular language captures. In formal terms, a regular language is any language that can be recognized by a finite automation, DFA, NFA, a machine with limited memory. You heard that right. Finite. It can't remember infinite stuff, but it can process patterns, recognitions, which means it's the foundation of text processing, compilers, and more. Now, how do we write or describe these languages? With something surprisingly elegant, regular expressions. If finite automata are the machines that walk through a string, regex is the map they follow. Let's say you want to match all strings that start with an A, followed by any number of B's. Regex would write that as AB. What does that mean? A starts with A. B, 0 or more B's. Boom. Just one line to describe an entire infinite set of strings, like A, AB, ABB, ABBBBB, and so on. You can build more complex patterns with or grouping. Regex is not just syntax. It's a symbolic interface between human logic and machine execution, providing a perfect abstraction. Easy to write, hard to misuse. Here's the magic twist. Every regular expression can be converted to a finite automation, and vice versa. That means that if you're building a spam filter using regex or writing a compiler that uses DFA, you're fundamentally doing the same thing, just from two different views, one mechanical, one algebraic. This duality is so powerful, it's like DNA and protein in biology. One is information, the other is behavior. Now, before you think regex can do everything, let me stop you. Let's say you want to design a regex that accepts all strings with the same number of A's and B's, like AB, AABB, ABAB, BBAA, but rejects AAA, BBA, and ABBBA. Sounds easy, right? It's impossible with regex. Not because you're bad at coding, but because it's theoretically impossible. Why? Because regular languages and their friend, DFA, have no memory. They can't count. To prove that a language is not regular, we use a mathematical weapon called the pumping lemma. Now, don't worry, we won't dive into its full formalism here. Just know this. The pumping lemma lets us show that a certain pattern cannot be processed by a finite automation no matter how hard we try. It's like a proof of limits, showing that some languages just live outside the boundary of regular land. You must be thinking, okay, regex is cool, but isn't it just for finding email addresses in code? Not at all. This deceptively tiny concept powers much of modern computing. Text search and pattern matching. From your VS Code Find panel, Control F, to grep in Linux, regex rules everything. Compilers and lexical analysis. The first step in building a compiler is tokenizing input. Regular expressions plus finite automata from the lexical analyzer, breaking your code into keywords, identifiers, numbers, etc. From validating and input sanitization. Ever submitted a form that yelled invalid email address? Yep, That was regex. Data cleaning and web scraping. Cleaning messy HTML? Extracting patterns from APIs? Regex is the scalpel. AI prompt engineering. Regex-like constraints are used in LLMs to navigate outputs into formats like JSON from natural text. Here's the truth. Regex and regular languages are not just a chapter in your CS book. They are the first line of defense and design when building any system that deals with inputs, structure, or syntax. And once you understand their power and their limits, you start thinking like a computer scientist. What is possible to compute? What patterns can we automate? Where does the machine fail to understand, and where must a human step in? Let's take a breath. So far, we've built machines, finite automata, regular expressions, even more and mealy machines. But here's the deeper truth. Machines follow languages, and they're not the ones you speak. They're mathematical languages, structured, precise, and layered. This brings us to something majestic, the Chomsky hierarchy, named after Noam Chomsky. Yes, the same linguist who revolutionized human language theory. This hierarchy tells us what kind of languages computers can understand, and more importantly, what kind of machine is required to process each. Imagine a building with 4 floors. Each floor allows more freedom in expression, but also needs a more complex machine to understand it. Let's go floor by floor. Type 3. Regular grammars, your bottom floor. This is the simplest kind. Think of street signs. Stop, no entry. They follow a strict pattern and limited format. Regular languages are just like that. They can be described by regular expressions and processed by finite automata. You've met them already. If your problem can be described with a regex, like email validation, lexical scanning and compilers, or finding keywords, you're in Type 3. Machine required, no memory, just transitions. Type 2. Context-free grammars, CFG. One floor up, these are like nested structures. Think HTML tags or balanced parentheses. A regular grammar can't handle nesting, but CFGs can. They use pushdown automata, which adds memory, a stack. A perfect example? Your compiler. It parses your code using CFGs to make sure your loops, functions, and scopes are well formed. It's like checking if each opened bracket has a matching closing bracket, even if they're inside other brackets. Machine required? A pushdown automation. It has a stack, like remembering where you left your tiffin box on a shelf. Type 1. Context-sensitive grammars. Now we're getting smarter. Here, rules depend on context. A word's meaning can change depending on its neighbors. Here's an example in English. I run every day. Versus the engine runs smoothly. In programming, context-sensitive rules help parse structures like variable inference or compiler optimizations. Unlike CFGs, this layer requires more powerful machines called linear bounded automata. Why? Because you can't just use a stack. You need memory proportional to the input. An analogy, it's like trying to understand sarcasm. The sentence alone isn't enough. You need context. Type 0. Recursively enumerable languages. Top floor. No rules, no limits. Any rewriting is allowed. This is the world of Turing machines, the ultimate computing model. If a problem is solvable by any computer, it lives here. But here's the catch. Many problems in this category are undecidable. We don't know if we can always find an answer, or if we'll loop forever. That's where the halting problem lives. Type 0 is complete freedom, but also maximum chaos. Now, you might be asking, why are we talking about all these levels? Because every programming language you use, Python, Java, C++, sits somewhere between Type 2 and Type 1. Every time a parser reads code, it's walking this hierarchy. Every AI that interprets a sentence, every compiler that checks for errors, every tool that validates structure, they all live in this pyramid. And here's the twist. Just because you can describe a language doesn't mean you can build a machine to process it efficiently. Now, are these layers watertight? Not quite. They overlap. For example, every regular language is also context-free, and every context-free language is context-sensitive, and so on. But not vice versa. It's like this: regular, context-free, context-sensitive, recursively enumerable. Some languages are so complex they require infinite memory or non-halting problems to decide. And that's where decidability breaks. Alright, time to climb one level up the ladder. Have you ever wondered how Google Docs checks your sentence structure? Or how a compiler knows a for loop ends exactly where it should? You're about to meet the unsung grammar police of the computational world: context-free grammars and their silent enforcer, Pushdown Automata. A context-free grammar, or CFG, is a set of recursing rewriting rules used to generate patterns of strings. Think of it like a rulebook, but one that defines the structure of programming languages, mathematical equations, or even human sentences. Let's say you're writing a code with nested if statements. Looks innocent, right? But did you know under the hood your compiler is battling ambiguity? That's where context-free grammar steps in. A context-free grammar is made up of 4 parts: variables like s, a, b, placeholders for patterns; terminals, actual characters or symbols like if, else, plus, or semicolon; start symbol, usually s, where everything begins; and production rules, like rewriting recipes: s if e, then s, else s. It's called context-free because the rules apply regardless of what's around the variable. The context doesn't matter. Now, let's generate a language using CFG. Imagine we have this rule: S goes to SB or epsilon. This generates strings like AB, AABB, AAABBB. For every A, we match one B. Balanced and nested. Neat, right? Now, when we apply rules, we can do it in different orders. A leftmost derivation always replaces the leftmost variable first. A rightmost derivation does the opposite. Both lead to the same string, but take different paths. This brings us to a parse tree, a visual family tree of how your string was born. Rooted at the start symbol, it grows down by applying rules until it produces your sentence. This tree is not just a pretty picture. It helps compilers check the structure of code. If the tree doesn't grow correctly, your code is invalid. But here's the catch. Sometimes a string can have more than one valid parse tree. That's ambiguity. For example, if E1, then if E2, then S1 else S2. Wait, doesn't that else go with the first if or the second? That's the dangling else problem. Ambiguity is bad news in compilers. It confuses the machine. So grammars must be rewritten to resolve this. Always give preference to one structure per string. No confusion. To make parsing simpler, we often normalize CFGs into special forms. With Chomsky's normal form, rules are broken down into 2 types: A, B, C, or A to small a. Greybach normal form, GNF, where every rule starts with a terminal. Why? Because normalized grammars are easier to automate and verify. Okay, so CFGs are powerful, but how do we recognize the languages they generate? Enter the pushdown automation, PDA. A pushdown automation is just like a finite automation, but it comes with a stack to recognize context-free languages. That's it, one little stack, but it changes everything. The stack gives it memory. Limited memory, yes, but just enough to match parentheses, track loops, or balance A's and B's. Imagine you're trying to validate A to N and B to N, or AABB. A simple DFA can't do this. It can't remember how many A's it saw. But a PDA? It pushes one symbol for every A and pops one for every B. If the stack ends empty and we reach the end of the string, accepted. Now, let's visualize a PDA. Start in a state Q0. On reading A, push A onto the stack. Stay in Q0. On reading B, pop A from the stack. Move to Q1. If the input ends and stack is empty, accept. This PDA accepts A to N and B to N, a simple yet non-regular language. Now here's something beautiful. For every CFG, there exists a PDA, and vice versa. This means the class of context-free languages can be recognized exactly by PDAs. So, if you write a CFG to generate code structures or build a PDA to recognize them, they're just two sides of the same coin. What if I told you there's a machine that can simulate any algorithm ever written? From sorting to solving math problems, the machine exists. It's called the Turing Machine, and it's the bedrock of modern computing. A Turing machine, TM, is a theoretical model invented by Alan Turing in 1936. It's a simple machine on paper, but its implications are universe-sized. It consists of an infinite tape divided into cells. Each cell can hold a symbol. A head that can read and write symbols and move left or right. A set of states including a start state and one or more halting states. A transition function mapping current state plus current symbol to new state, symbol to right, direction to move. It sounds modest, but curve this machine just the right way and it can compute anything computable. That's why it's known as the blueprint of all modern computers. Let's hand wave a reversal machine. 1. Copy the input onto the tape separated by a marker. 2. Move the head to the rightmost symbol. 3. One by one, rewrite the symbols in front of the marker, shifting left. 4. Eventually, the reverse string appears after the marker and we halt. Sounds slow, but it works on paper. Earlier, we saw that DFAs can't do A to N or B to N, but PDAs can. TMs? They can do that too, and more. On input AAA, BBB, a TM might mark the first A, move right, find the first B, mark it. Return to the next A, mark it. Repeat until all are matched. Except if all symbols are paired, else reject. No stack, nor shortcuts, just tape, head, and logic. The next point is crucial. The Church-Turing thesis asserts that anything that can be computed by a real-world algorithm can also be computed by a Turing machine, and vice versa. In plain English, everything you can program on your laptop, it can be done by a Turing machine. Everything a TM can do, it can be programmed on your laptop. They are computationally equivalent. Mathematically, it's our best faith in what an algorithm truly means. More like not having legit proof, but still an accepted foundation. In 1936, Turing proved something that shook mathematics to its core. There is no algorithm that can decide, for every possible program and input, whether that program will halt or run forever. That's the halting problem. Let me illustrate. Assume there's a magical program, halts PI, that tells us if program P halts on input I. We feed it a twisted version of itself that halts only if halts says it won't. Boom! Paradox. If it halts, it shouldn't. If it doesn't halt, it should. Conclusion: halts can exist. But why does it matter? Because this is the grand boundary of what machines can decide. From here, we divide problems into two camps. Decidable problems. TMs can always reach a yes or no answer after finitely many steps. Examples being prime checking, regular language membership. And undecidable programs. No TM exists that can decide all instances in finite time. Your examples? Halting problem, certain grammar equivalences, tilling problems. These are not just abstract cases. Security software can't guarantee detecting all malware, undecidable by nature. Program verification tools can't guarantee a complete proof of correctness for arbitrary code. Compilers use decidable subsets of features to say safe and predictable. Why does this matter? Because now you know the difference. DFA, tiny memory, shallow patterns. PDA, one stack, nested structures. TM, infinite tape, universal computation. We've moved from recognition to computation. From can you check this input to can you solve an arbitrary problem? Let's define our terrain. Recursive, decidable languages are like well-structured exams. For any input, the machine always halts and says yes or no. You get a definitive result every time. Recursively enumerable, RE, languages are trickier. If the answer is yes, the machine eventually halts and says yes. If the answer is no, it may run forever, leaving you in limbo. Think of a decidable problem like a vending machine. You insert coins and always get something, a drink or your refund, in finite time. An RE problem is like sending an email and waiting for a reply. If the recipient says yes, you know you got through. But what if they never respond? That could mean anything, not necessarily a no. Here are some examples. Decidable, recursive, checking if a number is even, sorting a list, membership in a regular or context-free language. Recursively enumerable, RE, checking if a Turing machine halts, checking if a program produces a specific output. This defines our computational reality. Recursive problems are safe, programmable, testable, reliable. RE problems are like black holes. They might never resolve. Let's zoom in on one fascinating RE problem not often talked about in undergrad CS. The post-correspondence problem, PCP. PCP setup. You have domino-like tiles. Each tile has a string on top and bottom. The question, is there a sequence of tiles, repetition allowed, such that the concatenated top equals concatenated bottom? Let's say you have these tiles. Tile 1, top, A. Bottom, AB. Tile 2, top B, bottom BA. Tile 3, top A, bottom A. Can you find a sequence of tiles where the strings on top match those on the bottom? So we might get a match. But imagine if this doesn't work. Or worse yet, you couldn't figure it out and the machine keeps running, just not telling you no. By cleverly sequencing them, you might end up with identical strings or get stuck trying forever. This is exactly what makes the post-correspondence problem undecidable. So why is this problem undecidable? Because there's no algorithm that can figure out for every possible case if a solution exists. In other words, there's no foolproof way to tell whether the tiles will match or not without running the machine forever in the worst case. PCP is an example of recursively enumerable problems, where you might eventually get a yes, but you might also be left hanging, never getting a no. It's like being in a never-ending email thread. Let's break it down one more time in a quick summary. Property. Recursive versus recursively enumerable. Recursive. The machine always halts with a yes-no answer. Example problems: checking if a number is even, sorting a list, membership in regular or context-free languages. Result for yes-no always halts in finite time. Implications: safe, predictable problems. Recursively enumerable. The machine may halt with a yes answer or run forever. Example problems: halting problem, PCP, checking if a program produces specific output. Result for yes-no may run forever, never saying no. Implications: might never resolve. In a world of computation, not all problems are equal. Some are decidable. You can always find a solution in predictable time. But others, they might leave you hanging indefinitely. Here's the truth you might not know. Antivirus and verification tools are dealing with undecidable problems every day. They might flag something suspicious, but they can't guarantee every threat is found. If a problem is undecidable, your only tools are heuristics, approximations, or constraints, but never perfect certainty. Understanding recursive versus recursively enumerable problems is like understanding the boundaries of what machines can and cannot do. And knowing these limits is crucial when it comes to designing algorithms, solving real-world problems, and even just being aware of what is computationally possible. Complexity theory. This is the wild world of computational complexity theory, where we don't just ask if something can be solved, but how long it would take. Time, space, effort, that's what we're measuring now. Welcome to the final frontier of theoretical computer science, where problems battle it out not to be solved, but to be solved efficiently. You're staring at a giant puzzle, with no image on the box, no edge pieces, just messy fragments that seem like they were never meant to fit. You could spend hours, days, maybe even a lifetime just trying to solve it. Now, hand that same puzzle to an average robot, not super intelligent, just an instruction-following machine. The question is, will it crack the puzzle in minutes, or will it crash trying? For this, we have computational complexity. It's all about measuring how long it takes for our machines to solve problems, and how much memory they need to solve them. But there's a twist. Not all puzzles are created equal. At its core, computational complexity is all about effort. How much time and memory it takes for a computer to solve a problem as the size of that problem grows. The bigger the problem, the more resources we need. Imagine a puzzle where the pieces keep multiplying as you try to solve it. The question is, how fast does the time it takes to solve the puzzle grow? Alright, let's get into the big players of complexity theory. P, NP, NP complete, and NP hard. These might sound like alphabet soup, but stick with me. Let's start with the good guys, class P, polynomial time. If a problem is in P, it means it can be solved quickly and efficiently in polynomial time, like O to n, O of n squared, etc., by a computer. Your examples: sorting list, finding the shortest path, checking if a number is even. This means that as the size of the problem grows, the time it takes to solve it only increases at a reasonable rate. Think of it like a pizza-making robot. If it takes 5 minutes to make pizza for one person, it might take 10 minutes to make one for 2 people. But the time doesn't explode the more people you add. It's pretty manageable. If you had to do this on a modern laptop or even a phone, no sweat, they scale nicely. Now, let's talk about the mysterious middle child, class NP, non-deterministic polynomial time. Here's a twist for you. You don't know how to find the solution quickly, but if someone gives you the solution, you can verify it quickly. Imagine you're in a maze and you don't have a map. But here's the catch. Once you find the exit, you can verify it immediately. NP problems are like that. You don't know how to solve problems quickly, but if someone shows you a solution, you can check it in a reasonable amount of time. So, NP includes problems where, while it might take a lot of time to find a solution, once you have it, you can verify that it's correct quickly. But there's a catch. NP complete. These are the hardest of NP problems. They're the ultimate puzzles, the ones where if you could solve any one of them quickly, you could solve all NP problems quickly. They're key to the universe, a special collection inside NP. Think of NP complete problems like a Super Mario boss battle. If you can defeat the hardest boss in the game, you can beat all the lesser bosses because they're connected in some way. In computational terms, if you figure out a quick solution for an NP complete problems, you've just cracked the code for an entire class of problems. Yeah, that's why people obsess over these. Find a fast algorithm for any one problem to solve them all. These problems aren't just academic. They apply to circuit design, drug discovery, delivery route optimization, and more. But wait, there's one more thing. NP hard. This is a bit of a mind-bender. NP hard problems are at least as hard as the hardest problems in NP. But they don't have to be in NP themselves. It's like the world champion in chess. You could be so good at chess that you're a master of all NP problems. But then you enter a new game, let's say quantum chess, and it's even harder. This new game isn't in the NP category at all, but it's still as hard as NP complete problems, or even harder. You might have heard this classic debate. Is P equal to NP? It's one of the Millennium Prize problems, and if you solve it, the Clay Mathematics Institute will hand you a legitimate check for $1 million. Right now, no one knows the answer. If P equals NP, it means every hard puzzle whose answer can be verified quickly can also be solved quickly. Which sounds amazing, but scary too, because it would mean chess, Go, and strategy games would be solved quickly. AI would skyrocket in intelligence. And not to forget, encryption systems would collapse. It would be like giving humanity an ultimate algorithm. But we still don't know. One classic problem is SAT, the satisfiability problem. SAT is the puzzle where you have a bunch of logical statements and you need to figure out if there's a way to make them all true at the same time. Think of it like a giant set of checkboxes. Your job is to figure out if there's a combination of checked and unchecked boxes that will satisfy all conditions. If someone hands you the solution, the right combo of checked, unchecked boxes, you can easily verify it. But finding that combo? That's the tough part. It's like being asked to check every possible combination of switches in a complex circuit. It could take a really long time. Another famous problem is the traveling salesman problem, TSP. Imagine you're a salesperson who needs to visit a bunch of cities and find the shortest route. You can't just fly straight from one city to the next. You have to figure out the best route that covers every city exactly once. But here's the catch. With more cities, the number of possible routes explodes. If you had 4 cities, that's just 24 possible routes to check. But with 10 cities, that goes over to 3.5 million routes. The more cities you add, the worse it gets. Which is exactly why this is an NP hard problem. And here's the Cook-Levin theorem, the breakthrough that ties all this together. SAT was the first problem proven to be NP complete by Stephen Cook and Leonid Levin in the 1970s. That's why you call it the Cook-Levin theorem. They showed that if you could solve SAT quickly, you could solve all NP problems quickly. Since then, we've found thousands of problems that reduce to SAT, where we can turn them into SAT problems and solve them if we had a magic SAT solver. But again, no one has found that magic solver yet. P is inside NP. NP overlaps with NP hard. NP complete is at the intersection of NP and NP hard. Let's remember, in real life, when Google Maps optimizes its routes, it's approximating TSP. When your antivirus checks for malware signatures, it's solving complex problems related to SAT pattern matching. Even scheduling your final year timetable is an NP hard task. We use heuristics, smart guesses, approximation algorithms, randomized algorithms, and machine learning shortcuts. So here's the thing. The real limits of AI, security, and automation don't lie in hardware or even in data. They lie in theory, in the mathematical nature of problems themselves. We're not just building faster machines. Rather, we're chasing a deeper truth. What is truly solvable and what forever lies beyond our grasp? That's why complexity theory is the compass of future computing, rather than just being some geeky obsession. Let's start rewind mode, fast. We started with finite automata, the simplest form of machine intelligence. Like traffic lights, they're rigid, rule-based, and efficient, but limited too. Then came regular expressions, showing how search engines or form validators understand your daily life patterns, all backed by math. Next, we climbed into context-free grammars, the kind that powers your compiler, the unsung hero behind every run button you hit. Along the way, we saw how ambiguity is not a writing problem, but a programming nightmare. Enter pushdown automata with a memory stack, where suddenly machines aren't just reacting, they're remembering. That one step unlocked a whole world of nested languages, like matching brackets or parsing functions. Then we unleashed the Turing machine, the GOAT, the model that doesn't only simulate what computers can do, it defines what computation even means. That's where we met the halting problem, the eternal glitch that even the smartest algorithms can't fix. And along the way, when we thought we understood solvable, we faced the truth. Some problems can't be solved. Ever. Enter undecidability. Not due to tech limits, but due to logic itself. Think about that. Finally, we zoomed out into the universe of complexity. P, NP, NP complete, NP hard. The unsolved puzzle that decides whether you can solve problems fast or just verify fast. From FSMs to PDAs to Turing machines and beyond, the theory of computation is not just computer science. It's philosophy, logic, and a reality check of our own limits. We've journeyed from the simplest machines to the edge of what's computable and even beyond into the unsolvable. The theory of computation isn't just history or math. It's the map of our digital universe, charting both the highways of possibility and the walls of impossibility. So, next time your code compiles, your search finds the right answer, or your AI completes your thought, remember, all of it traces back here. If this gave you clarity or even more questions, stay with us, because every week we peel back another layer of computer science, faster and clearer than any textbook. Don't just use machines, learn how they think. Don't forget to like the video and subscribe. Thanks for watching.